Okay, so last time we were talking about stoichiometry. We talked about how to do sort of basic stoichiometry problems. And remember, with sort of basic stoichiometry problems, if you want to kind of think about it that way, it's really a situation where you're only given one piece of information, about the actual chemical equation that you're dealing with. So maybe you're told how much products you're making, maybe you're told how much reactants you're starting with. Um, and in those sort of basic stoichiometry problems, there's really kind of four steps that you follow. Obviously, with any sort of stoichiometry problem, you always want to make sure you are starting with a balanced equation. So that's definitely the first step, no matter what. The second step as well, no matter what, usually is you do need to convert whatever they give you into moles. So very common, obviously, is you're given the information in grams and using the molar mass to convert it to moles. But again, you could be given that information in any type of unit. So the ultimate end goal of sort of the second step is to get yourself into moles. And the reason for that is really the basis of stoichiometry, which is it's really a conversion factor that, as we talked about, you basically get from the actual balanced equation, you get from the coefficients from the balanced equation, and those are what are referred to as the mole to mole relationship. So for all the units to properly cancel out, you got to make sure you obviously get everybody into moles so that you can then actually go to the equation and find the two things you're interested in. One thing, again, is what they gave you. The other thing is sort of what you're trying to find and find the multiple relationship. And that really is the stoichiometry part. That is really kind of the conversion factor part. It allows you to, again, go from the piece of information they gave you, which is ultimately not what you're looking for, to somebody else in the equation, which is what you're looking for. And that multiple relationship, which is nothing more than the coefficient in the balance equation, which is why step number one is really important to make sure that you obviously start with a balanced equation. Will allow you to do that. And really the fourth step is to convert, those units. You will always be pretty much in moles at that point. And if you are looking for moles, then you would be done with the problem. If you're not looking for moles, then you may have usually one conversion, maybe it's from moles to grams, for example, or again, you may have multiple conversions to get it to the proper units. So balance equation, convert to moles, mole to mole relationship, and convert moles to some other unit are really the four steps that you should always just kind of repeat as you're doing these basic stoichiometry problems. What makes it a basic stoichiometry problem, as I mentioned, is that you're just given pretty much one piece of information. If you're given two pieces of information, for example, that probably will end you up in a limiting reagent type problem. So we talked about limiting reagents. Limiting reagents are the reagents that get used up first in a chemical reaction. The one that you have plenty of is what is referred to as the excess reagent. And in those type of problems, it is always the limiting reagent that determines how much product that you would produce. So in a limiting reagent problem, you can identify it, as we talked about, by you are given enough information uh, to be able to calculate the moles of both reactants, for example. So again, maybe you're given grams of both reactants, maybe you're given some other units, but the ultimate way that you could sort of recognize it as a limiting reagent type problem is just that whatever information that is given to you is enough information for you to basically get to the units of moles. So if you look at your reactants, you could get to the units of moles for both of those, then it definitely is a limiting reagent problem. As we talked about, there's many different ways that you can kind of solve a limiting reagent problem. Again, one way is to just do two separate stoichiometry calculations from each reactant to the product. Whichever one produces the less amount of product is your limiting reagent. The other one would be your excess reagent. You could also do a stoichiometry calculation between the two reactants where you try to determine, do you have enough of one reactant to use up the other reactant? And if the answer is yes, when you do that calculation, then that's the excess reagent. The other guy would be the limiting reagent. If the answer is no, then that reagent would be your limiting reagent. In both of those problems, obviously in that problem, you then would do the calculation using the limiting reagent to figure out how much product. The main way that I sort of showed you was maybe a new way for a lot of you. and that was the ice table approach, where we have initial, change, and end. Initial, basically, in the ice table approach, is just the starting moles of your reactants. We could assume that 0 would be the starting amount for your products. We do the change part, and again, the change part's important because it is what allows you to basically do the stoichiometry of it. So initially, right, you would have the moles of this guy and the moles of this guy and nothing for that guy. Change, we would do minus 2x. Again, a reminder in this example here, 2 comes from the coefficient. That takes care of the multiple relationship. Minus, because we would expect reactants to be decreasing with time, minus 3x. 3 also from the coefficient, also a reactant. And remember, on this side here, we would be doing plus x. Again, we should be expecting products to basically be increasing. We carry everybody down, as we did a number of occasions. We then would set each of the reactants equal to 0. We solve for x, and x would equal the number of moles, and pretty much all these x's here. We're looking for the smallest x value. All right, so the smallest x value would be your limiting reagent, and the larger one would obviously be your excess reagent. So when you figure out whichever one's the smallest x, again, that pretty much is every x in this sort of table here. And again, some of the benefits that we talked about of sort of doing it this way is a lot of times you are asked questions like, how much maybe of both products would be produced. You may be asked how much of the excess reagents left over, which is a very common question. And again, by doing this sort of table, you have everything sort of set there that you can very quickly pretty much answer all those questions within like 1 step or 2 steps. And, without maybe having to go all the way back to the beginning and start a kind of separate calculation from the beginning to calculate those things. Remember that when we do talk about sort of reactions, what we are producing, or what we calculate that we produce from the actual equation, is what is referred to as the theoretical yield. And that went with the other thing that we talked about, which was the percent yield. Percent yield is the actual divided by the theoretical times 100%. And textbook type problems, again, the actual yield is usually given to you. So somewhere in the problem, they'll say you actually yielded this much or produced this much of the product. Theoretical yield is, as we were just talking about, basically from the equation and your starting amounts, how much product you would produce. And again, that's based off the limiting reagent always. And obviously times it by 100, there gives you your percent yield. So as we mentioned last time, percent yield, we are looking for a large number is good, small number not so good in the percent yield sort of arena there. Also, really large number over 100%, also not so good usually, because that usually does indicate some type of error probably took place. We finished up talking about solutions there last time. And solutions, remember, there's 2 parts. There's the solute, which is the smaller part, and there is the solvent, which is the larger part of a solution. And a solution is, again, those guys that get that aqueous symbol next to them. And when we talk about solutions, one major thing that we talk about is concentration. And the most common unit of concentration is molarity, which is big M. And it is moles of solute over liters of solution. And really, most people just kind of go moles per liter. You can kind of think of this almost as a formula, because we use it a lot of times like a formula. And again, if you have 2 of the 3 pieces of information here, you could solve for the others. So sometimes you may want to solve for liters, which would be moles divided by the molarity. And a lot of times we do solve for moles, and that would be liters times molarity. So these are sort of 3 rearrangements of the molarity sort of definition there. again, kind of used as a formula very commonly. And again, this is one that we use a lot along the way. Now, it's important also to remember that, as we talked about, it's a good idea if you have something given to you like that 4.5 molar sodium chloride to, when you're doing calculations, sort of get rid of the big M. And as I mentioned last time, it's a lot of very common mistakes when people don't do that, is they end up forgetting all about sort of the volume part of it, or where it is, and should you be multiplying, should you be dividing, type of thing. So a lot of times it's a good idea to just change that number into sort of this version of it, where the number stays with the moles. It's always per 1 liter, and really think about sort of molarity, as a conversion factor. And again, you can use it through a dimensional analysis sort of type of calculation. And again, you'll be able to clearly see the volume part. And again, that's a very common one people kind of screw up and sort of mess up on. Any questions on that stuff that we talked about last time there? Okay, so I guess where we left off was, I think, at dilutions is where we're at. All right, so another very common thing that we do with solutions is we do dilutions, basically. And a lot of times solutions come in very concentrated sort of form, and a very concentrated sort of solution, which means, for example, it has a very high molarity. So a lot of times they come in what are sometimes referred to as stock solutions. Stock solutions, usually means that it is very concentrated, has a very high molarity. And a lot of times we don't want to use them like that. We want to use them in more dilute solutions, like, for example, over here. And one way that we do that is through a process called dilution, and basically we add more solvent. So a lot of times that solvent is water, but it doesn't always have to be water, because water is not always the solvent. So we add more solvent to it, or more water to it, basically. And what that does is it makes that solution more dilute. As you can see over here, count the circles. I'm assuming the same number of circles on both sides. The important part is, though, the solute, which would be represented by the circles here, is basically the same before and after the dilution. So really the only thing that we're doing is basically adding more solvent. So how does that affect the molarity? Well, if we think about what we just talked about in terms of what molarity is the moles of solute divided by the liters of solution. And since the solution, as we just mentioned, is basically the solute plus the solvent, when we go through the process of diluting, we're basically adding more solvent. So we're basically adding more of this guy, which, if we look at our molarity expression, is here, and we're basically increasing this number. So when we increase that number in terms of the bottom number, just mathematically speaking, when we take a small number divided by a larger number, the molarity goes down, right? You get a smaller number. So the process by which we add more solvent when we're doing a dilution causes the concentration to go down and become less, obviously, concentrated. Again, it's kind of like when you get like a very big drink with a lot of ice in it, and maybe you go somewhere, leave it somewhere, and all that ice begins to melt and starts to melt a little while down the road there. When you come back and you drink your soda there, again, it's not as strong and fresh, if you will, there as it was when you first got it out of the fountain. Obviously, all that ice that has melted added more water to it. It kind of watered it down, and it's become more dilute. So the same idea here. Technically speaking, whatever you had in terms of syrup and all that other stuff that's in your soda was still the same, beginning and end. The only difference was that water was added from the melting ice. And again, the same idea here is we just add more water or solvent, and that's the only thing that we're doing, and decreasing the molarity in that particular case. So there actually is a a formula that goes with dilution, and it is M1 V1 equals M2 V2, or these are initial and final. Most people will use M1 V1 equals M2 V2. This is really the dilution equation. And M1 here is the molarity of the more concentrated solution usually. M2 V2 is the more dilute solution. Doesn't necessarily have to be. That's usually the way it is, though. And we use M here, which is molarity. V is volume. And we use the molarity here again because it's the most common sort of unit of concentration. You will sometimes see people you call the dilution equation a little bit different. They'll use something like C1V1 is equal to C2V2. It's basically the same thing. The only difference is here C is just a generic term for concentration. So what that means is, although we oftentimes sort of use molarity all the time, or most of the time, there are other units of concentration, some of which we'll talk about here, some of which we'll talk about a little bit later on in another chapter, but things like percent mass to mass, percent mass to volume. You could use molality, some other type of units and stuff like that. So generically speaking, the C's there represent concentration, V still represent volume and stuff like that. So typically speaking, again, M1, V1 is kind of your stronger, more stock solution. That's kind of like before the dilution. And M2, V2 is your dilute solution, which is sort of after you do the dilution in that case. Now, when we use this specific equation, when we use M1 V1 equals M2 V2, there is a little bit of difference in terms of how you could do the calculation when you're using molarity and volume and using this equation versus when you're using just molarity and volume by itself. So when we're solving for example, moles, you do need to take the liters times the molarity. So when you're using molarity all by itself, not in a dilution situation, you do need to convert the volume into liters in order for everything to cancel out correctly, in order for you to really get moles. So in a standalone problem that's not a dilution, you're doing something with concentration, something with molarity, you should always convert the volume into liters. One place where you do not need to do that necessarily, you could do it if you like, but you do not need to do it necessarily, is in using this equation. You can leave the volume in milliliters here. And that's the volume on both sides. You can leave them in milliliters here, and it will work out okay. And the reason for that is, I might have mentioned, I think maybe we're going to talk about molarity, is really moles per liter. And that definitely is what molarity means. It could also take the definition of millimoles divided by milliliter. And what that means is when you take a volume that's in milliliters and you times it by molarity, you do not get moles. You actually get what are referred to as millimoles. So over here, when we take the volume in liters and times it by molarity, we get moles. But when you take milliliters times molarity, you get what are known as millimoles. And in this use of this formula, it's okay because, for example, if we were solving for M2 would be M1 V1 divided by V2. That should be a 1 there. There we go. And when we do this, if we just put the units in, if we decided to take molarity times milliliters divided by milliliters, if we did the top, as I just mentioned, molarity times milliliters gives you millimoles, not moles. And on the bottom is milliliters. The actual millis there will cancel out and return you to moles per liter, which is molarity. So specifically speaking, and only in this situation, you can leave the volume in milliliters as long as it's milliliters on both sides. V1 and V2 is in milliliters. If you want, you could absolutely convert V1 and V2 or whichever V you may have into liters. Then you will have moles, and you don't have to worry about it as well. But you can definitely leave it in milliliters when you're using this dilution equation. You absolutely 100% should convert the volume into liters if you are not using this formula. You're just using molarity by itself. Any questions on that there? So other important things about what some of these things mean, again, as we talked about, M1, V1 is before dilution, M2, V2 is after dilution. V1 typically means in this situation how much of the more concentrated solution you're going to take out. V2 is basically the final volume of the diluted solution that you're going to make. All right, so why don't you try one here, see what you come up with. So how would you prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock 4 molar nitric acid solution? So take a minute or two, see what you come up with. Look at it just to make sure everybody's on the same page here. So we want to prepare a 60 milliliter solution that is 0.2 molar, and we want to do it from a stock solution that is 4 molar. So in this particular case, we can basically pull out the information there, but let's kind of draw it to make sure everybody's on the same page. We should have a bottle that is sitting there, and this is our stock solution over here. That is basically 4 molar. What we then want to do is figure out how much of that we should use to make a new solution that has a volume of 60 milliliters total, and also has a molarity of 0.2 molar. So we basically want to figure out how much we should take out of the 4 molar to put in there to make the solution. So we can definitely use our dilution equation, M1 V1 equals M2 V2. Here, going with the assumption that the 1 should be the stronger sort of concentration, that is this guy. So that means M1 is 4 molar. V1, we're not sure. We do know we want to end up with a concentration of 0.2 molar and a volume that is 60 milliliters. So here we can see that we would be solving for V1. And if we do that, V1 would equal M2 V2 over M1. In this case, M2 is 0.2 molar. V2 is 60 milliliters. Again, here I can leave it in milliliters. It's okay in this particular case. Again, if you want to convert it to liters, it's perfectly fine. You would put in there 0.06 liters. It will come out the same in this case. We're going to divide by our 4 molar. Again, the reason why it works out okay is you just look at straight units here. That's molarity divided by molarity. Basically cancels out, leaves us with milliliters as our units in this case. So if we do that, taking 0.2 times 60 divided by 4 gives us 3 milliliters. So V1 here would equal 3 milliliters. So what does V1 really mean in terms of the 3 milliliters? Well, what it means is that's actually 3 milliliters of nitric acid. And more specifically, that is 3 milliliters of this nitric acid over here. So basically we would take out of there and dump into our new beaker or flask, whatever it may be, basically 3 milliliters of the nitric acid. Now, when we think about it though, I need to end up with a 60 milliliter total of solution. So the rest is going to be water that's going to be added. Should I add 60 milliliters of water to the solution? And it's a very common thing that people will do. And the answer is no, you should not do that, because if you added 60 milliliters of water to this, that's 60 milliliters plus the 3 milliliters you already put in there would give you a grand total of 63 milliliters instead of 60 milliliters. So in this particular case, we want to make sure we get the proper amount of water. And very much a very common question that's asked in dilution problems is just that: how much water should you add? So we can figure that out by usually using our equation as well to figure out how much water we should add. And that basically is, in most cases, V2 minus V1. That's our final volume minus our initial volume. The difference there would be the amount of water that would be added, our solvent, if we're not dealing with water, obviously. And in this particular case, we see that our final volume is 60 milliliters. We already know we're adding 3 milliliters of the nitric acid to it. And if we take 60 minus 3, that is 57 milliliters of water should be added. So to this solution, we then should add another 57 milliliters of purple water here to this solution. The 57 milliliters of water, the 3 milliliters of nitric acid gives us a grand total of 60 milliliters, which is what we're looking for. So at this point, what we would do is mix it up and stir it really well. And what we should end up with now is a solution that has a concentration of 0.2 molar. Any questions on that there? So again, that's a very common sort of dilution question is, how much water should you add? So make sure you do read the questions sort of correctly here, so that you do answer what they're asking. So the question is, how do you know how to solve for volume one? In this case, we originally knew we needed to solve for volume one, if that was your question, based on the information that was given to us. And you definitely will not always be solving for volume one. But in this case, if we look at it here, if we just look at the concentrations, since we were given both concentrations, we have sort of a larger concentration and a smaller concentration. So these are our M values. And again, typically speaking, you don't have to do it this way, but typically speaking, the M1 is the more concentrated solution, the higher number, and the M2 is the smaller number. And since this volume goes with the second concentration there, we know that this is going to be V2. As long as you keep, honestly, the volume and the concentrations that go together, you could call it M1, V1, or M2, V2. It doesn't really matter. Work out the same mathematically. But that's how we knew in this case. We basically had this number, and this number given to us. We obviously were missing this, so that's why we knew we needed to solve for that. But again, you may not always be solving for volume, you may be solving for molarity as well. Other questions? And obviously, typically speaking, because in most cases people do make sort of the ones here, the more concentrated number or the higher number. Typically when we're solving for V1, we're talking about how much of the stronger guy we should take out to add to our new solution, like we did over here. And typically speaking, when we solve for V2, because most people make the twos kind of the dilutes part of the calculation, we're solving for sort of the final volume. But realistically speaking, as long as you keep the volume molarities together, you could label them any way you want. But that's sort of what we knew we were solving for. So for example, here, let's take a look at, go back this way. So let's just say we had a, we'll do a, no, it's more. Let's do a 16 molar nitric acid solution. So we had, let's do 125 milliliters of a 16 molar nitric acid solution. What would be the molarity of the solution if we added 200 milliliters of water to it? All right, so take a moment and see what you come up with here. I'll do it as well since I made up the numbers. Look at this one again. Let's kind of draw it to see what we're dealing with here. So we got this guy here, which is 125 milliliters and is 16 molar, basically solution. And in this case, we're actually going to be adding some water to it. Water. And we're basically going to dump in there another 200 milliliters of water. So I guess I'll put this on the outside, actually. 16 molar. This was originally 125 milliliters. So when we look at this, we have a couple of things sort of given to us. First off, we see that this number here and this number is most likely what we're starting with. So that's our M1 is 16 molar. V1 is 125 milliliters. M2 is what we're looking for. And V2 in this case is actually not going to be 200, which is a common mistake, because in this case, our final volume is the 200 we just added of water and the original 125 that we started with, which means our new solution's volume actually would be adding those together, and 325 milliliters is actually our second volume and not 200 milliliters, which is a common mistake people would make. So again, you need to understand sort of what's happening when we're doing a dilution. If we add water, that's basically the solvent in this case. And basically that means that this new solution that has a new molarity is what we get when we mix all this together. And as to sort of the earlier question, in this particular case, we're actually solving for M2 versus a volume, which again is a very common thing as well. In this case, we would use M1 V1 is equal to M2 V2. Solving for M2 would give us M1 V1 divided by V2. And again, here, we do not need to change it to liters, but if you want to, you can. But we can leave it here in milliliters. And we could do that because our total volume, our correct total volume, is 325 milliliters. Again, milliliters and milliliters will cancel. That's going to leave us with molarity as our unit, which is good because that's what we're looking for. And that means we end up with actually 16 times 125 divided by 325 gives us, we'll call it 6.15 molar. So we do see the concentration here go down to 6.15 molar by doing this dilution. And again, our total volume is a result of the 125 we started with of the acid plus the 200 milliliters we added. Any questions on that particular one there? Our dilutions in general. So it's really important to carefully read dilution type questions and again, understand the process of dilution, because as you can see here, if you're just going to go automatic and go, oh, I have a volume and a volume that's given to me, so obviously those are the correct volumes. Again, like that very common mistake, people would use 200 milliliters here instead of the proper number. Questions on that one there? Okay, so now we talked about sort of molarity, concentration, and we talked about dilution. We're going to kind of put those guys together here and talk about a couple of things. We're talking about some other sort of stoichiometry type problems and procedures that are used where basically stoichiometry does come into play. One sort of procedure is gravimetric analysis, which is kind of what we see here in this problem. And in this sort of pictures on the bottom, gravimetric analysis basically is a process where you make a solid. So again, kind of similar to that silver chloride empirical formula experiment where, you know, we had some silver, we added some acid to it, and we ended up making a solid. That's a very common sort of procedure. Another common procedure is to just take two solutions and mix them together. And the result of that is a precipitation reaction, which forms a solid precipitate. And you can then filter out it, dry it, weigh the precipitate, and you can figure out the basically percent yield that you got. And that would be your actual yield. And that's what we see here. Here we have basically one solution there on the bottom. We have another solution over here. As we mix them, again, you can see the precipitation forming. At this point, we're going to have a precipitate. Obviously, we still have a good amount of solution left over as well. We're not really interested in that solution. So as you can see, the whole beaker gets really cloudy white over here. So what he's doing is pouring it through here. This is a vacuum filtration, basically in this particular case. The liquid part goes through. We'll highlight it this way, as you can see down here, which is what we're not interested in. Sort of the white precipitate there. Again, not looking like a solid or anything like that, but it's kind of floating around in there. The white precipitate would end up here up on the filter paper. And obviously, as we talked about as sort of sources of error and sort of percent yield, this type of procedure is a very common one where you can get basically a lot of error, and it's basically resolving right around here, as we mentioned, I think last time as well. If you do a process such as something like this, and you're kind of in a rush, that filter paper is basically soaking wet from all the liquid part that went through it. If you decided not to let it dry out and you weigh it, you're going to have all that extra water weight, and that's where you can find yourself over 100% yield, which again would not be a very good thing. What you'd want to do, obviously, is take that filter paper, maybe put it in drying oven, just let it sit for a day or two until it really dries out really good. And what you would be left with, hopefully, is just a precipitate by itself that's dried. And once you do that, that would be your actual yield. And an actual experiment there is actually how much you produce. Knowing the equation, you could basically do a stoichiometry problem to calculate the theoretical yield. Now, when you look at the setup here, though, when you would do a stoichiometry problem, it may be a little bit different. And maybe a little bit different than a traditional stoichiometry problem where we start with grams and then go to moles. In this particular case, it's a solution and a solution, which means we're probably not going to go with grams to moles in this case, but we probably know perhaps the molarity of this guy. Maybe we know the molarity of that guy. Maybe we only know the molarity of this guy, one of them, and there's an unknown. But if we know the molarity and we know the volume, for example, we can use molarity is moles per liter, and we could solve for moles by taking liters times the molarity. And in sort of stoichiometry that involves sort of solutions, that's a very common sort of procedure. At that point, you could do your basic kind of stoichiometry steps. You could obviously have a balanced equation. You can convert to moles. And again, using sort of volume and molarity to convert to moles. You could do your mole to mole relationship, and you could obviously convert moles into some other units. By the way, if you happen to know the molarity and the volume of this guy in the graduated cylinder, if you happen to know the molarity and the volume of this guy in the beaker, that means in both of those cases, you can figure out the moles of both of them, right? And that means that this could be a limiting reagent problem as well. So you definitely could have a limiting reagent problem where you're using two solutions, you're using molarity and volume on both of them. And again, if you have that enough information to get to moles, then you do have to figure out the limiting reagent. So that's what I was talking about earlier, that, we want to think about it in terms of, do I have enough information to get me to moles of each reactant? And that can be done in many ways. It could be done traditionally by going grams to moles. So you have the grams of both of them. But in a problem like this, we would have perhaps the molarity and volume of each of these solutions. And that also would allow us to get to moles of this guy and moles of that guy, which would then technically make that problem, if we were doing a stoichiometry problem, a limiting reagent problem. So that's why it's important. The way I sort of say it is, you want to think about, do I have enough information to get to moles? However you can get to moles, do you have enough information to get to that moles? And if the answer is yes, then obviously you would need to do a limiting reagent problem. So you would do a stoichiometry problem, either a regular stoichiometry problem, limiting reagent stoichiometry problem. That would get you your theoretical yield. Obviously, if you did this and weighed out the final amount that you got, that would be your actual yield. And you could put that together with the percent yield that we've been talking about, actual divided by theoretical times 100%. And you could actually calculate in an experiment like this, for example, how good you did there by what your percent yield would be. So this is gravimetric analysis. Again, it's usually was used when you make some type of precipitation reaction or precipitate, and you're interested in really, how much you produce and all that kind of stuff. Another very common place where we use stoichiometry is in kind of solution stoichiometry or straight solution stoichiometry, and that is where we do a titration. And when we do titrations, a titration is a process where a solution of known concentration is kind of added slowly to a solution of unknown concentration. And again, because all the information about one of the solutions, that allows you to use stoichiometry to figure out what you're interested in the other solution. So typically when we do a titration, we use what is referred to as a buret, which you can kind of see the bottom part of it here. That's a buret. And a buret really is nothing more than just a really long glass sort of tube, if you will. And obviously at the end, as you can see here, it comes down and you can kind of basically let things drip out of the bottom. There's kind of like an on-off switch here, which is referred to as a stopcock here. And it basically opens and shuts, basically. And if you open it, this would be open position, by the way. That allows obviously stuff to drip out the bottom. It has a lot of labels on it. One important thing about a buret is a wonderfully bad drawing here. But if you get to the very top, for example, very top is 0 milliliters. We fill it from the top, it comes up, it goes out the bottom, and it actually increases in numbering as you go down. So that would be 1 milliliter in my example, say 2 milliliters, 3 milliliters, and so forth. So when you read a buret, for example, let's just say your solution was filled to here. A lot of times people will read this incorrectly. They'll go, oh, it's above the 3, so it's 3 point something. But remember, it is dropping out the bottom, which means we actually read it going down, which means that this right here would be, for example, 2.5 milliliters. So it actually increases as you go down and not 3. So that's a very common mistake when people read burets, is they read it incorrectly. The other really wrong thing that people do is that they will fill it to the 0 mark and they will call it like 50 milliliters or 25 milliliters, depending on the volume of the burette. So again, 0 always at the top when you use a burette, increases as you go down. You want to make sure you always read it correctly. And in most cases, when you read a burette, 2 decimal places is where we read it to. So for example, if we have a solution that's up here, and let's just say it was, let's say, a sodium hydroxide solution, and we know the molarity of it. So if we know the molarity of our sodium hydroxide solution, and say down here we had some type of unknown acid. And the only thing that we know about this acid is the volume. Let's just say we had 25 milliliters of it. We could continue to add this, say, base to the acid in this case, and we typically will continue to add it when we do a titration until we reach what is referred to as the equivalence point. And the definition of the equivalence point is the point where basically the reaction is complete. And when we talk about like an acid-base titration, which is a very common titration that we do, in an acid-base titration, when we reach the equivalence point, that is the point where exactly the moles of the acid that's present will equal exactly the moles of the base. So in this particular example, this was sodium hydroxide, this was an unknown acid. When I reach that equivalence point, that would be the point where I have added exactly the same amount of moles of sodium hydroxide as my unknown acid moles was there. How do I know when I've reached the equivalence point or the reaction is sort of done? I know that because I usually will add an indicator when we do a titration. When we do a titration, we add an indicator. An indicator gives us a visual reference as to, hey, you should stop your titration. It is actually something that will change color near the equivalence point. And when you see that color change, you should stop your titration. You're done with your titration, and you hopefully did a good titration. Now, the equivalence point is really what you're shooting for, but sometimes you'll hear the term endpoint. An endpoint of a titration basically is where you lay up your titration, go, I'm done. I'm pretty much done with it. If you do a really good titration, your endpoint and your equivalence point should be pretty close to each other. You don't want to stop your titration way before your equivalence point. You don't want to stop it way after your equivalence point. You want to kind of stop it right there, kind of at your equivalence point. So how does that all work? Well, for example, we would add some indicator to our solution in the flask. So this is like the bottle indicator there. It most likely is an indicator known as phenolphthalein, which is a very common indicator. Put a drop or two into here. And when you do, as you can see at the start of the titration, there's no color. It's colorless. And that is because indicators, for example, like phenolphthalein, actually work over a pH range. So typically indicators, especially when you're doing acid-base titrations and indicators basically work over a pH range. For example, phenolphthalein works over a pH range of like 8.3 pH to 10 and change. And if you're familiar with the pH scale goes from 0 to 7 to 14. Above 7 is basic, below 7 is acidic. So you can see that at 8.3, what we see in terms of color for something like phenolphthalein is it's actually colorless. And as you kind of move this way, I don't really have that color, I don't think, but as we kind of move-ish this way, it starts to get pink. Pretend my red is pink. Then as you get this way, it gets really, really pink. Pretend again my really dark red is really pink. So as we sort of move this way, it goes from a very light pink to a very dark pink. So it would sort of make sense, as you kind of see here when you do the titration. When you start, there's no color because what we have in here is an acid, which means if it's acidic, the pH has to be in this range, which is less than 8.3, and that's why it's still colorless. When we start doing the titration, it will turn this really light pink color. And that is ultimately what you're shooting for, especially when you're doing a titration that uses phenolphthalein. You typically would do it because it will turn light pink around the equivalence point. And what that tells us is, in most cases, when we're using something like phenolphthalein, our equivalence point is somewhere in this region, kind of where that colorless to super light pink kind of occurs. And that's why we want to stop when you see the first tinge of pink. When we talk about using phenolphthalein, that tinge of pink, we're talking about like you got to hold up a white piece of paper or something underneath it to actually see the pink color. If you get super, super dark pink, that's really bad because that probably means you're way down here and perhaps in pH. And that means you perhaps have jumped way past your equivalence point and you maybe missed the equivalence point. So it's a very interesting use of an indicator. You have to kind of be careful as you're doing it. If you've ever done a titration, for example, that has used phenolphthalein, maybe you have, maybe you haven't, I don't know. There's a very common thing that people will sometimes say when they kind of do the titration is like, hey, I just added 1 drop, of say the base. And it went from like no pink color, colorless, to like super dark pink. 1 drop just made it be no color to dark pink. And you may think to yourself, well, I kind of jumped way too far. And it may not always be the case. So sometimes people get really sort of hung up on the color when they're doing titration, especially say using something like phenolphthalein, that kind of no color to light pink to dark pink color. And in most cases, if you're really careful as you're doing the titration and you're adding kind of drop by drop and you're going really slow, and if you just add 1 drop and it shoots you from like kind of like no color, it's really dark color, you're probably okay. And the reason for that is what is really happening in terms of pH when you do a titration and you reach the equivalence point. So again, this is something that you'll learn more about in 200B, but just a preview it for you, maybe help you understand why that might occur. If we do what is sometimes referred to as a titration curve, where you graph the pH, say volume of sodium hydroxide added in an acid-base titration, you'll typically get a typical sort of S curve, which looks something like this. And this is what is referred to as a titration curve. And let's just say your equivalence point is about here. So as we're adding the sodium hydroxide, we typically see 2 things occur. As you get closer to the equivalence point, we see a pretty good jump in pH to the equivalence point, and we see another jump after the equivalence point in terms of pH. And that's why they'll tell you, when you're using something like an indicator and you're dropping your sodium hydroxide, you'll see that pink color, for example, stay for a bit and then go away as you kind of mix it. Stay for a bit, go away. And as you're approaching the equivalence point, you'll see that pink color kind of stay for a longer period of time, and then it will go away. And it'll kind of stay a little bit longer, and then it'll go away because you're kind of mixing it as you're adding constantly. And that's what tells you that you are getting close to the equivalence point, and it kind of gives you an indication that you should kind of go slow at that point, as this kind of the pink color staying longer and longer and longer. But what we see at the equivalence point is when you get to the equivalence point, really, and no matter what type of titration that you do, it goes pretty vertical. And what does that mean? Well, if we were going vertical here, that means that, if you had a pH up here, our pH here, the pH changes a lot right? It changes a lot. In a very small volume, because if you follow the volume down, no matter kind of where you draw that line, it's all going to hit pretty much the same spot. So as we approach the equivalence point, a very, very small volume has the effect of changing the pH a lot. And what that means is when we're using an indicator like phenolphthalein that goes from like a pH of 8.3 to like a pH of 10ish, by adding that one drop, it may actually send us from this kind of no color to this sort of dark color of pink. Again, imagine that's pink and dark. And just by that one drop, because again, doesn't take a lot of volume to change the pH of that solution a lot. And if you're going very carefully, what I'm saying is it really doesn't matter. The total volume matters. Where it is a true issue is if you're really not being careful. So if you're not being careful and you're like, I'm just going to open that thing up and just let this thing maybe not go by drop, but let it just stream in, right? Because I got places to be and I'm just looking for a pink color. If you're really not being careful and you're just letting this thing flow into the flask, for example, from the Buret, what you could find yourself is like over here, for example, in terms of volume and pH. And that's also going to be really dark pink, right? But the difference is you're way away from your equivalence point, which is way back here. So if you're not really, really careful and you're just letting it flow really fast, you definitely could jump way past the equivalence point and not really be near it in terms of volume. If you're going really, really slow and being very careful about it, kind of drop by drop and stuff like that, especially when you get near the equivalence point, even if your color is not like super light pink, but darker pink, you actually will still be okay in terms of your calculations. If you just let it open it up and flow really freely and really jump way past it, your calculations are going to be significantly off. So sometimes in, say, 200A, for example, when you're in person doing this type of experiment, they beat it to your head. You got to get light pink, super light pink, barely see the pink. If you didn't, then you should start all over. And the reality is you don't necessarily always have to start all over. More important that your volumes when you reach the equivalence point, if you do multiple trials, are about the same. And that probably is correct in that sense. Definitely you should do it again if you just open it up and really aren't careful and you just shoot way past it and stuff like that. Any questions on titration there? So how do we use sort of this information to help us figure out things? Well, we use this information to figure out things by really doing stoichiometry. And again, here we would follow the same sort of 4 steps for a stoichiometry problem: our balance equation, our convert to moles, our mole to mole relationship, and again, our units. The only difference is in a couple of these steps, the balancing equation is the same. Step 2, where we convert to moles. Again, here we are using solutions in most cases. So in most cases here, we would be doing our moles is equal to our liters times our molarity. So that again is a very big difference in terms of what happens in sort of a titration or solution stoichiometry is how we get to moles. So no grams to moles in a lot of cases. The mole to mole relationship really would be the same. And the other difference is when we do sort of these titration or solution stoichiometry problems is the last step where we take the moles to some other unit. A lot of times we may be interested in what is this guy's concentration, which means you may use molarity on the back end of your calculation to calculate something like molarity of the solution. So slightly different, same steps, really, same 4 steps. The difference is, again, we would use molarity perhaps on both parts of the calculation to try to figure it out rather than, again, molar mass. Any questions on any of that there? How do I know it's a titration problem? Well, a lot of times, for example, if it's involving acid or bases, it may say titration. It may say something like how much is required to neutralize one thing versus the other. Remember, neutralization, acid-base neutralization reaction. These are all sort of words that indicate basically a titration problem, and basically you need to sort of do stoichiometry. So why don't we try one here? Why don't you give it a try and see what you come up with, and we'll talk about it and make sure you're hopefully on the right page. So again, follow the same 4 basic stoichiometry problem here. And again, you have some volumes and some solutions, so you're going to calculate a little bit different, but we're looking for what volume of 1.42 molar sodium hydroxide is required to titrate 25 milliliters of 4.5 molar sulfuric acid. So visually, I'll give you sort of what is happening here. We are adding the sodium hydroxide to the sulfuric acid. So we're adding this way. So why don't you take a couple minutes based on what we were just talking about, see how far you get and see what you come up with, and we'll talk about it here. Okay, let's take a look here and kind of see how we're doing. So remember a couple of important words, obviously titrate here, so it tells us it's titration. Again, other common ones, especially dealing with acid and base titrations. And by the way, you could definitely have titrations that do not involve acid and bases. That's the most common sort of titration that you do is an acid-base titration. But believe it or not, you can do a titration involves sort of a precipitation reaction and stuff like that. So most of the time, usually dealing with acid and bases, but again, titrations don't always have to necessarily involve sort of acid and bases in that sense. It is going to be basically a solution stoichiometry problem. So again, we really just want to follow the 4 steps and sort of treat it here like a basic stoichiometry problem. And we know it's a basic stoichiometry problem because, again, we could go to our sort of rule where do we have enough information to get the moles of each sort of guy? We do have enough information to get the moles of this guy, but definitely don't have enough information to get the moles of the sodium hydroxide. So again, it does default to a basic stoichiometry problem because of that. Now we do have H2SO4, which is a acid, plus our sodium hydroxide, which is a base. So we have like a strong acid, strong base problem here. And if you remember from our talk of that, when we take a strong acid, strong base, we get 2 things. We basically make salt and water here. This is basically a double displacement reaction like we talked about. That's a positive negative guy, positive negative guy. Remember that when we take an acid and base, the OH from the base, the H from the acid is what's going to make our water. The salt will result from the combination of the other 2 things, which in this case is sodium and sulfate. Remember that sodium is +1, sulfate is -2, which means when we put those guys together, the proper formula is Na2SO4. Again, in this case, we want to make sure that we get the correct formulas like we talked about when we're talking about types of reactions, and we want to make sure that we now balance it, right? So now that we got everybody there in terms of their correct formulas, it's important to balance it. So I think perhaps a 2 there will do it, and a 2 there. So this is basically step number 1. Any questions on that so far? Step number 2 is to take whatever they gave us and convert it into moles. Remember, as I just mentioned a second ago, by looking at what they gave us, we really only have enough information to get to moles for this guy. So that's really where we want to start. So really what we're doing in this problem is we have enough information about moles of this guy. We then want to get over to basically the sodium hydroxide. So the next thing that we want to do is convert to moles of our sulfuric acid. Again, we're going to use the molarity and the volume to do so. A couple important things. First off, obviously molarity is our moles per liter, which means, again, moles would be liters times molarity. So first off, we do need to convert this into liters here. And if we do that by dividing by 1,000, or just moving our decimal place over, that does get us to 0.025 liters. Timesing it by our molarity here, when we see 4.50 molar, that is the same as 4.50 moles per liter. We're going to use this as a conversion factor in dimensional analysis, which means 4.50 moles per liter of sulfuric acid. Liters will cancel each other out, and we will end up with 4.5 times 0.025. Looks like 0.1125 on that. 0.1125 moles in this case. And again, this is sulfuric acid. Any questions on that? If we analyze sort of the pieces of information that was given to us, just to make sure here, obviously, as we just saw, we were given the molarity and the volume of this guy, which would allow us to get to moles. In terms of the sodium hydroxide, we are given a piece of information. We are given 1.420 molar. So again, if we think about the molarity, which is moles per liter, and we're looking for the volume of sodium hydroxide, that means that we need the molarity, which was given to us for the sodium hydroxide, and we need the moles. So this part here, the moles of the sodium hydroxide, is going to come from the stoichiometry here. So we want to then do really step number 3, which is our mole to mole relationship. And again, in this case, we're interested in sodium hydroxide, but we only have enough information about sulfuric acid. And from the equation, we could see that for every 1 mole of sulfuric acid, you get 2 moles of sodium hydroxide. So we're going to use that like a normal sort of stoichiometry problem here to go from moles of sulfuric acid to moles of sodium hydroxide, which is really what we're interested in. So we'll put that guy up on top and 1 mole here on the bottom. Moles of the sodium the sulfuric acid will cancel. We're basically going to times this by 2, going to give us 0.225, looks like. Moles of sodium hydroxide. And that is, again, the stoichiometry part, just like we've done previously. At this point, we are not interested in grams or anything like that, like we've done in many stoichiometry problems up to this point. We're actually interested in the volume. So now that we have the moles of sodium hydroxide and we have the molarity of it, we can now basically convert our moles into liters, basically, our volume. And using the molarity equation, we see again that liters is equal to moles divided by molarity. And that means that we have 0.225 moles of sodium hydroxide. I'm going to use the molarity of sodium hydroxide like a conversion factor. And that means that I have 1.420 moles per liter of sodium hydroxide. I'm basically dividing by my sodium hydroxide here, but showing it dimensional analysis way, divided by 1.420, going to give me 0.158. The units here would be liters of sodium hydroxide, which I could then times by 1,000, convert it into milliliters, which would be 158 milliliters of sodium hydroxide. So basically what we just calculated was you need to add 158 milliliters of sodium hydroxide in order to reach the equivalence point in this titration. Any questions on any of those steps? hopefully you can kind of see it is really like a traditional sort of basic stoichiometry problem. Again, really the differences here is how we get the moles and what we do with the moles on the back end of the calculation there as step number 4. Any question on that particular one there? All right, so I want to try one more here. Oops. Let's see. If it took 35 milliliters of 0.35 molar potassium hydroxide to neutralize 25 milliliters of hydrochloric acid, what is the molarity of the hydrochloric acid? All right, take a couple minutes to see what you come up with on this one. And to end here, let's take a look and see how we're doing. So again, this is another way sometimes a titration problem sort of worded, or solution stoichiometry problem is worded. So here we took 35 milliliters of 0.35 molar KOH to neutralize 25 milliliters of HCl. What is the molarity of the HCl? Again, just visually sort of what's happening up in the Buret is our KOH in this case. Again, down here would be our HCl. We're adding our KOH to our HCl. Again, if we know we're going to need an equation, so that's going to be hydrochloric acid, which is a strong acid, KOH, which is a strong base. Again, we're going to get our water coming from the OH and the H, and our salts, which is going to come from obviously the other two guys that are left in this particular case. We want to make sure it's balanced. So in this case, I believe it is. So we got 2 hydrogens, 1 chlorine, and 1 potassium on each side. So we're good on all of those things there. All right. So obviously now that we have it balanced, we want to think about sort of the information that's given to us. If we just kind of pull out the information, we see that for HCl, we have 25 milliliters, and we are looking for the molarity of it. Here we have 35 milliliters, and we're looking at 0.35 molar. So again, out of these two guys, which are reactants, we really only have enough information to get to moles of KOH. We don't have obviously enough information to do that. We are looking for the molarity here. So it is going to be just a basic sort of stoichiometry problem. The idea here is we eventually want to get to the molarity of our HCl. In terms of that, we actually do have the bottom part. It's in milliliters, but we do have it in terms of liters we can convert it to. We are missing the top part here. So that's really where we want to kind of get to. That's where stoichiometry is going to come into play. So the second thing is to convert into moles. We're going to convert our KOH into moles in this case. We are going to convert our volume into liters here. Divide the 35 by 1,000. We are then going to use our molarity of our KOH as like a conversion factor, 3.5 moles per liter of KOH. Liters will cancel each other out, which is why we do need to make sure we convert it into liters here. And if we do that, we do end up with 0.1225 moles of KOH. Again, we're not really interested in KOH. We do want to go from KOH to HCl. So that is where the third step comes in our mole to mole relationship. Third step is our mole to mole. In this particular case, for every 1 mole of HCl, we get 1 mole of KOH. That makes it fairly simple here. That means that 0.1225 moles of KOH using that as a conversion factor, 1 mole KOH, 1 mole of HCl, they cancel each other out, 0.1225 moles of HCl. That is the top part here that we needed. So now we have really both of the information that we need. We're not going to use molar mass here, but we are going to use the molarity as moles per liter. The moles that we just calculated, which is 0.1225, divided by the volume, which again, we do need to convert to liters by dividing by 1,000 or moving the decimal point over, gives us that guy right there. So the question is 3.5 moles in step 2. I'm not sure where I got that from. I guess I read it wrong, so thank you very much. So let me go back and correct that. Thank you. I got the numbers. I just got the point in the wrong spot there, huh? So that obviously is going to move some numbers around here. So let me just erase some of these numbers. So I'll fix them real quick. Thank you. Here, double check. Or maybe I typed it in right and just wrote it wrong. Let's just make sure. So this obviously for the KOH was 0.35 moles per liter. So 0.35, try that again, times 0.035. That should give us 0.01225. So that would then make this guy 0.1225. And obviously make this guy 0.01225. And now we should be at 0.01225 here. Thank you very much for letting me know that. All right, so just to make sure one more time, so 35 divided by 1,000, 0.035 times 0.35, 0.01225 moles, 1-to-1 relationship. And now we're down here. So we're going to divide at this point 0.025. Units will not cancel. It gives us 0.490 moles per liter, or 0.490 molar HCl. There you go. Thank you very much. So yeah, sorry about that. I wrote it wrong there. So that should be 0.35. And again, just add a 0 basically coming down. Question on any of those steps there? Okay, so these are titration problems. You want to make sure, A, that you write it correctly, apparently, and also you want to make sure that you do follow these steps and you do write the equation and stuff like that, especially when you're doing anything involved stoichiometry. You want to make sure, again, you do have that equation written. Little note here before we finish it up here for lecture is, again, talking about an equation that we saw earlier, which is M1V1 equals M2V2. And sometimes people will use this dilution equation for titrations. And in some cases, you'll get it right. In other cases, you will not get it right. It will work okay for here, and you really shouldn't do it. But it would get you the right answer here. And it's only because of this that it's a 1-to-1 relationship that it comes out correctly. If you try to use that on our previous problem, because it's not a 1-to-1 relationship, it will not come out correctly. So I highly recommend that you don't try to do that where people do it all the time. Is try to use this for titrations. You should only use it for dilutions. You should really write out the equation. You should make sure you balance it correctly and get the right relationship. So don't fall into that trap where, again, sometimes people just continuously use the dilution equation for titration problems and stuff like that. And a lot of times they will get it incorrect because the multiple relationship is not 1-to-1, so it will not work out correctly. Any questions on that there? Okay, so we will stop here for lecture right now.